We hear all the time about machine learning doing amazing things, right? Like predicting what movies we'll like or even the stock market. And the accuracy is incredible. But a lot of these models, like neural networks or those random forests, they kind of feel like magic boxes. You see them spit out these awesome results. But trying to figure out how they got there, it's a total mystery. So today, we're going to dive into some research that's trying to tackle this whole issue of intelligible models. Basically, can we have models that are not only super accurate, but also transparent? Models we can actually understand and check and even tweak if we need to, especially in fields like healthcare, where trust is so important.
Yeah, definitely. It's like we've had to pick between accuracy and understanding for so long. You either have this super accurate black box model that's a total enigma, or you have a simpler one that's easy to understand but might not be as good at predicting things. This research we're looking at, they're proposing these generalized additive models with pairwise interactions, or GA²Ms, and the big finding is that these GA²Ms can actually be as accurate as those complex models out there while still letting us understand how they work. Like they showed it can predict things like how likely someone is to die from pneumonia or end up back in the hospital, all while being totally understandable and even editable.
So our goal today is to really break down how these GA2M models work, why being able to understand them is such a big deal, and what kind of cool insights we can get from them. We want to basically open up that black box without losing any of its power.
Right. And to really grasp this, let's go back to this important study from the 90s in healthcare. They were trying to use machine learning to predict the risk of death from pneumonia. And back then, neural networks were all the rage and were actually the most accurate, getting an AUC of 0.86 on one of the data sets.
Just to clarify for our listeners that AUC, it's basically a score of how good the model is at separating the people who will have the outcome, like dying from pneumonia in this case, from those who won't. So closer to one means better at separating.
Exactly. And in this study, they compared the neural networks to the more traditional logistic regression, which got an AUC of 0.77. So the neural network looked way better on paper,
But
right?
they didn't actually end up using the neural networks, even though they're more accurate, did they?
Nope. And there's a good reason for that. So alongside the fancy neural networks, they also used a simpler rule-based system. This system wasn't as statistically impressive, but it had one major advantage. You could understand its logic. It learned these clear-cut rules. And one rule it found was, if a patient has asthma, the risk of dying from pneumonia is lower.
Wait, that doesn't sound right, does it? You'd think having asthma would make things worse.
And you'd be right, usually. But what this rule actually uncovered was a quirk in the data. See, in this data set, pretty much all the patients with asthma and pneumonia were sent directly to the ICU and given very aggressive treatment. And this treatment was so effective that it actually made their risk of dying lower compared to everyone else with pneumonia in that data set.
Oh, I see. So it wasn't that asthma was protecting them. It was the special care they got because of it.
Precisely. And the key thing is, because the rule-based system was transparent, this weird finding about asthma was obvious and raised a red flag. But with the neural network, there was no way to know why it was predicting what it was predicting. It could have been picking up on this same misleading correlation or even other problematic patterns in the data, and no one would be the wiser.
So even though it had better stats, the neural network was basically a black box. They couldn't trust it in a life or death situation because they didn't know what was going on inside. It's like, if you don't know why a model says someone is high risk, how can you use it to make decisions about their care?
Exactly. The researchers back then chose to stick with the less accurate but more understandable models, like logistic regression. At least they could see what those models were doing and potentially fix these weird associations like the asthma one. This just shows why, when it comes to important things like healthcare, being able to understand the model isn't just a nice bonus. It's absolutely necessary if you want to trust it and keep things safe.
So fast forward to today, we've got even fancier machine learning models, but they're still mostly black boxes. That brings us to these generalized additive models, or GAMs, which you said are kind of a gold standard for intelligibility. How do these GAMs actually work?
Well, think of a GAM as a way to predict something by looking at how each feature individually affects the outcome and then just adding those effects up. It's like, okay, this is how much feature A matters, this is how much feature B matters, and so on. And then you combine all those individual pieces to get your prediction.
So it's kind of like looking at each ingredient in a recipe and figuring out how much each one contributes to the final taste.
That's a good way to put it. It's all about breaking down the prediction into these separate, understandable parts.
So then what are the downsides of using GAMs? If they're so good for understanding, why aren't we using them all the time?
The catch with standard GAMs is they assume each feature acts independently. They don't really capture how features can interact and change each other's effects. Like imagine you're trying to predict the price of a used car. A basic GAM might just look at the age and mileage separately. Older car, lower price. Higher mileage, lower price. But what if you have a really rare classic car with high mileage? It's probably still worth a lot more than just subtracting the mileage penalty from the price you'd expect for a car that old. There's something special about that combination of age and mileage in this particular case.
So the whole is greater than the sum of its parts sometimes. And that's where these GA²Ms with those pairwise interactions come in, right? They build on regular GAMs to account for these interactions.
Yeah, exactly. GA²Ms add in terms that specifically model how pairs of features interact. So for our car example, it wouldn't just look at age and mileage individually, but also at the combined effect of having a certain age and mileage together. It would recognize that high mileage might mean different things depending on whether it's a regular car or a rare vintage one.
And you're saying these GA²Ms are still understandable even with these added interaction terms. How does that work?
Well, the beauty of it is you can visualize these interactions. The model learns a function that describes how the interaction between two features affects the outcome, and you can actually plot this function. Like you might see that when feature X is high and feature Y is also high, the risk of something happening increases way more than you'd expect from just adding up their individual effects. It's something you can actually see and wrap your head around.
So it's not just a bunch of numbers. You can actually see the patterns. Okay, so let's jump into those real-world examples. The first one you mentioned was predicting the risk of death from pneumonia. What can you tell us about that study?
They took this data set of about 15,000 pneumonia patients, and they had 46 different features for each patient. Things like age, gender, medical history, results from physical exams and lab tests, even what they saw on chest x-rays. The goal was to predict how likely each patient was to die from pneumonia.
And how well did the GA²M do in terms of accuracy?
It actually had the highest AUC of all the models they tested. It got a score of 0.857. For comparison, logistic regression got 0.843, random forest got 0.846, and even the regular jam was a bit lower at 0.804. So the GA²M wasn't just interpretable, it was also the most accurate in this real-world medical problem.
That's pretty impressive. It sounds like it's really bridging that gap between accuracy and interpretability. But you said the real power of GA²Ms is being able to understand them. What kind of insights did it reveal about this pneumonia data?
Well, here's where it gets really interesting. By looking at the individual terms in the GA²M model, the researchers could actually see how each feature was influencing the risk of death. For example, when they looked at age, unsurprisingly, they saw that, in general, risk increases as people get older. But they could also see more nuanced patterns, like the risk was pretty stable for people under 50, then it started going up gradually, and then after 66, it really shot up. They even saw some potential jumps in risk around ages 67 and 86.
Wow, so you can actually see these specific points where the risk changes more dramatically. That's much more informative than just knowing that older people are generally at higher risk.
Yeah, exactly. It's not just a straight line. And remember that asthma issue from the 90s study? Well, the GA²M also found this weird association where having asthma seemed to lower the risk of death from pneumonia in this data.
Oh, right. So the GA²M picked up on the same misleading pattern as the rule-big system back then, but this time it wasn't hidden inside a black box.
Exactly, because they could see all the parts of the model, they could spot this potentially wrong association with asthma right away, and then they could use their medical knowledge to figure out why it was probably happening, the aggressive treatment those patients got. And then they could decide how to deal with it in the model, like maybe adjust the asthma term or include other factors to get a more accurate picture.
That's amazing. It's like you can actually debug the model using real-world knowledge and clinical experience. What other interesting patterns did the model uncover?
Well, they also looked at this thing called BUN, which is a measure of kidney function. The model showed that when a patient's BUN level wasn't measured, their risk was lower. This probably means that doctors weren't ordering this test for patients who seemed healthy. On the flip side, high BUN levels were linked to higher risk, which makes sense because it can be a sign of kidney problems, which can complicate things. And the model also very clearly showed that people with a history of cancer were at a much higher risk of dying from pneumonia, which again aligns with what we know about cancer potentially weakening the immune system.
And you said there were also some surprising findings about chronic lung disease and chest pain.
Yes. Similar to the asthma thing, the model initially showed that having chronic lung disease or a history of chest pain was actually linked to a lower risk of death. And the researchers thought this might be because these patients get more proactive and intensive medical care because of their existing conditions. So again, being able to see what the model was doing allowed them to spot these unexpected findings and figure out what might be causing them.
It sounds like the GA²M is almost acting like a super smart detective, highlighting these subtle patterns that you might miss with just a statistical black box.
That's a great way to think about it. It's like it's pointing out clues that we can then investigate further. They even found this weird thing with heart rate data. The model's representation of how heart rate related to risk had this strange shape, and when they dug deeper, they found there was a whole chunk of missing data for heart rates between 40 and 120 beats per minute. Apparently, all of the patients in that range were just marked as normal in the data set, so the model helped them uncover a potential data quality issue that they might not have noticed otherwise. And then for features like breathing rate and body temperature, where we have a pretty good understanding of how they relate to illness, the model showed the expected patterns. Higher breathing rates and extreme temperatures, both high and low, meant higher risk.
Now, what about interactions between features? Did they find any important combined effects in this pneumonia study?
Oh, yeah. One really striking example was the interaction between age and having cancer. The GA2M showed that the highest risk was actually for the youngest patients who also had cancer. And this probably reflects how aggressive some childhood cancers can be and how that interacts with a pneumonia infection, making those kids especially vulnerable. It's a nuanced relationship that you wouldn't see if you were just looking at age or cancer history on their own. The main takeaway here is that the GA2M didn't just predict well, it helped the researchers understand why it was making those predictions, which is so important in healthcare.
That's really cool. Now, you also talked about a study on predicting if someone's going to end up back in the hospital within 30 days. That sounds even more challenging because of how much data is involved.
Oh, yeah, that was a huge data set. They had almost 200,000 patients in the training set, and each patient had almost 4,000 different features. Things like lab results, notes from doctors, their whole history of hospitalizations, all sorts of stuff.
Wow, with that many features, how can you even begin to understand what a model is doing? It seems impossible to look at each feature and interaction individually.
Yeah, that's where things get tricky. Instead of trying to analyze all those 4,000 features and their interactions at once, the researchers focused on understanding the model's predictions for individual patients. They looked at the top contributing factors for patients who the model thought were very likely to be readmitted, and they compared those to the factors for patients who were at average risk. What they found was the GA2M could give a clear and concise explanation for each individual prediction by highlighting the most important factors for that particular patient.
Can you give an example of what that looked like for an actual patient?
Sure. So for one patient who the model predicted was very likely to be readmitted, the most important factors were the sheer number of hospital visits they'd had recently, like 40 total visits, and 19 of those were inpatient stays in just the past year. That's a lot. Plus, there were signs of an ongoing infection based on the meds they were on and some hints of potential heart problems from other meds. Another high-risk patient, the key factors were all these specific chemotherapy drugs they'd been given. So that suggested they were getting pretty aggressive cancer treatment, which unfortunately might not be working so well and could lead to complications that land them back in the hospital.
So even with thousands of possible things going on, the model could zero in on the most relevant factors for each person's risk.
Exactly. And then for a patient with a moderate risk score, the factors that stood out were things like having a treatable type of cancer, a benign tumor, and being on muscle relaxants, but also having normal blood counts and not many outpatient visits. It painted a picture of someone with some health issues, but not the same level of immediate concern as the high-risk patients. This ability to understand individual predictions is super valuable for doctors because it helps them make sense of the model's assessments and use that information to make better decisions for their patients.
That's really powerful. You also mentioned this challenge of finding those important interactions when you have so many features. It sounds like a huge computational problem to figure out which pairs of features are actually interacting in a meaningful way.
You're absolutely right. With thousands of features, the number of potential interactions is just enormous. To deal with this, the researchers came up with this clever method they called FAST, which stands for Fast Interaction Detection.
I like that name. Very fitting. So how does this FAST method help find these key interactions so quickly?
The basic idea is that instead building a full-blown interaction model for every single pair of features, which would take forever, FAST just quickly estimates how strong the interaction might be. It does this by creating these super simple interaction models using just a few strategic cuts in the data for the two features being considered. It's like a rough sketch to see if there's anything interesting going on between those two features. And by doing this for all possible pairs, FAST can rank them based on how strong the interaction seems to be.
So it's kind of like a super efficient filter to find the pairs of features that are most likely to have a real impact without having to waste time on all the less promising ones.
Exactly. And the research showed that FAST is not only fast, but also surprisingly accurate at finding those important interactions compared to much slower methods.
Hmm.
This is key for making these GA2Ms work in the real world with these massive data sets.
You also briefly mentioned this thing called feature shaping. What's that all about?
Ah, yes. Feature shaping basically means that the GA2M can learn these more complex, curvy relationships between individual features and the outcome. It's not stuck with just straight lines like some simpler models. And this is important because in the real world, relationships are often not so simple. Like we saw with age and pneumonia risk, it wasn't a straight lineup. It was more like a curve with different slopes at different ages. GA2Ms can capture those nuances, which makes them more accurate than models that just assume everything's a straight line or rely on these simple categories for things that are actually continuous.
One last but super important point. We've been talking about these models finding links between certain features and outcomes, but that doesn't automatically mean one thing causes the other, right? Correlation doesn't equal causation.
Absolutely. That's so important to remember. GA2Ms are really good at highlighting strong patterns in the data, but they're still based on observing associations. Just because we see a strong link between, say, having a certain gene and getting a particular disease doesn't mean that gene directly causes the disease. There could be other factors we're not seeing that are influencing both. However, what's great about GA2Ms is that they allow us to formulate better questions about causation. We can see these strong correlations and then use our knowledge and intuition to investigate what might be going on underneath and design studies specifically to look at cause and effect. With black box models, you just don't have that ability to dig deeper.
So, wrapping it all up, it sounds like these GA2Ms are a really big deal in the world of machine learning. They're paving the way for models that are both accurate and understandable, and that could be a game changer in fields like healthcare where trust and transparency are so important.
I totally agree. The really exciting thing is that we might not have to choose between accuracy and interpretability anymore. Being able to not only predict things, but also understand why those predictions are being made opens up a whole world of possibilities. We can validate our models, catch and fix potential errors or biases, and actually learn something new from the data. Like that asthma example, being able to understand why the model was making that weird connection and then figure out what was really going on. That's something you just can't do with a black box.
It makes you wonder what other hidden patterns we could uncover if we had this kind of transparency in other fields like finance, criminal justice, or even climate change. There's so much potential here. And for anyone who wants to learn more, the research paper itself goes into all the details. They have visualizations of the model's terms, a full explanation of that fast algorithm, and a lot of discussion about the implications of using intelligible AI in fields where the stakes are high.
Yeah, it's definitely worth checking out. And maybe the biggest question of all is, can these intelligible models like GA2Ms lead to a better, more collaborative relationship between humans and AI? Can we work together to solve some of the really tough problems facing us today? It's a really exciting thought.